Hello again everyone, welcome back to ptet.chemistry channel. My name is Dr. On, and in this tutorial video, we'll go through these particular practical questions on thermometric titrations. So in between these thermometric titrations tutorial, I'll include in the experimental procedures that allow me to collect the set of results that we will analyze later on. This is a reaction between a base, which is a potassium hydroxide. The base is the proton acceptor because it accepts H+, and then the acid is the proton donor. It donates the H+. H+ does not have any electrons. It does not have any neutrons inside the nucleus. It only contains the proton. That's why H+ is called proton. That's why acid is called proton donor. It donates H+. And then the base, it accepts the H+, and then the OH- add together with the H+, you get H2O. This is your classic ionic equation for any neutralization equation. You always come back down to these H+ plus OH- giving you H2O liquid. And as such, we are not breaking any bond. Instead, we are forming a covalent bond, and that is why neutralization is an exothermic reaction, because there is no bond being broken, and we are just forming the covalent bond between oxygen and hydrogen, and this is just bond formation, which is exothermic. It means that the system releases heat to the surrounding, the system loses heat energy to the surrounding, and when the surrounding is your solution is going to get hotter. So the temperature of the surrounding, which is the solution, is going to increase, and there is something that we will observe in this particular, well, in fact, in any exothermic neutralization reaction. So in these experimental procedures, as you will see me doing the actual procedure, is that we have a beaker, and then inside the beaker we support the plastic cup, and in there we're going to put a thermometer, and this thermometer allows us to read the initial temperature of the solution before we mix in the other one. In this particular case, we have P, which is the potassium hydroxide, and we pipette 25.0 cm3 of P. Because pipette has this much accuracy, we don't just write 25 cm3, we write 25.0 cm3. Pipette, you need to spell correctly, P-I-P-E-T-T-E, and then you pipette 25.0 cm3 of P into here. So what we have inside there is actually P, and then temperature, the initial temperature is to be read to the nearest 0.5 degrees Celsius. The same thing you will deal with any temperature kind of experiments. Our thermometer records up to 0.5 degrees Celsius, so that means something 0.0 or something 0.5 degrees Celsius. You gotta include that in the laboratory reading. Now record the value in column E. So for the first experiment, you pipette out this much volume of P, so this is what you pipette out. And then the Q is from the burette, and you will see that throughout you pipette out the fixed volume of P into the plastic cup, and then you keep on changing the volume of Q from the burette. So you need to know the initial reading on the burette, as well as the final reading, which of course depends on how much volume you want to pass from the burette into this measuring cylinder, which you're going to top up with water. This plus this add up to 25. Each of these, the volume of Q plus the volume of the water there, which is your distilled water, is going to add up to 25.0 according to this instruction here. You put Q into the burette, you put 5.0 cm3 from the burette of the Q into this measuring cylinder, and then that means if you top it up to 25 cm3 on the measuring cylinder, you add distilled water. You never use tap water because tap water contains dissolved ions, and distilled water is just pure water until the total volume of liquid is 25 cm3. You mix them together, you mix Q, pour Q into P, and then the temperature will rise. You had the initial temperature earlier, now you have the final temperature. The change in temperature is going to be final minus initial temperature, but the biggest mistake that student will make is that you forgot about the nearest 0.5 degrees Celsius. So that means you must have a 0.0 or 0.5, which your calculator will not show you when it's 0.0. Therefore, you need to keep an eye out for these. You repeat this experiment following the volume of Q, and you have to top it up to 25 cm3 in the measuring cylinder as well. That one is easily done. Just make sure you use a drop-in pipette when you're close to the 25 cm3 mark, because you add drop by drop towards the end. Just like when you want to pass out 10.0 from the burette, you would try to do it drop by drop when you're close to this 10.0 cm mark, and therefore you will be adding an exact amount. That's called accuracy. Okay, so I'm just going to append in, I'm just going to put in the experimental video where I actually do this experiment procedure to collect the results. This is called thermometric titration. Thermometric, something to do with thermal, something to do with temperature. We're going to be using thermometer to measure temperature change essentially, or calculate temperature change from the temperature that we measure using thermometer, and this will enable us to work out or determine the end point for this titration. That's why it's called thermometric titration. Without further ado, let's get started. So what do we have here? So this is the question. So I'm not too sure if I will be able to do the picture-in-picture, but what P is aqueous potassium hydroxide, Q is sulfuric acid. So P is potassium hydroxide, and P has to be pipette out. This is a pipette, P-I-P-E-T-T-E. So I pipette P out, and I pipette 25.0 cm3 pipette, 25.0 cm3 pipette of P, which is potassium hydroxide, into a plastic cup supported in a beaker. So the plastic cup here actually refers to this styrofoam cup. Styrofoam is this kind of like soft surface thing, S-T-Y-R-O-F-O-A-M, styrofoam cup. It's pretty unstable on its own, so that's why we have to support it on a beaker. Now we're gonna pipette that out. So before we use the pipette, we always have to rinse it with distilled water, but the one you're provided in the exam usually is pretty clean already. I'm just gonna take that extra precaution and rinse it with some distilled water. So I've got some distilled water on the outside. I have to wipe it dry first before I pipette out a little bit of P, because I will have to wash the pipette, rinse the pipette with the solution that you're going to fill it in. So this is P, goes in the pipette. I would have to wipe the outside a little bit clean, so that I'm just doing the S, which is sucking out the solution. So I'm going to rinse the pipette with the solution that I'm going to fill it in. I don't need a lot, I just need to do rinsing. Okay, so that was done rinsing. Even when you are doing an actual titration, the usual titration with the indicator, you also have to do something similar. So it has the S and the E and the A buttons. The A basically is what you use in order to compress the air, and then you're gonna stick this empty pipette now into the solution and then press S, and then I usually personally prefer to do it at a slight angle, so I'm holding this at a slight angle. Somehow it just feels a bit faster, but don't know about you. Once it's there, you can see there is a line around this region here, so I have to press E in order to get 25.0 cm3, and I have overshot that, and this is just, no, that doesn't look alright. That one is alright. Okay, I'm gonna eject a little bit, and now this is 25.0. This is a burette, B-U-R-E-T-T-E. You know this run from 0 to 50.0, 1 decimal place for all level and IGCSE level. But of course, if you are A-level students, you know that you need to do burette rating to 2 decimal place. I'm just going to focus on the 1 decimal place because I am specifically preparing this tutorial video for the O-level and IGCSE level 14 to 16 years old chemistry students. Before you use a burette, I typically always wash the burette with a little bit of distilled water. Make sure you wash the bottom as well, and then roll it out and remove all the distilled water. But just like the pipette, you also have to rinse it with the solution that you're going to fill it in here. I will have Q in the burette, so I put a little bit of Q in here, just a little bit for washing. Okay, I don't need a lot for washing, so it will take around 5 cm3 then. Make sure you allow it to pass through the bottom because you're washing the bottom bit with this solution as well. White background behind it. 22.0. Yep, you can hopefully see the silvery line now. Well, it's not really silver inside, it's actually I think it's mercury inside. And what happened then is you got 20 at the bottom and you got 30 on top. So you're reading from the bottom to the top. There's 21 and 22.0 to the nearest 0.5. There's 22.0 degrees Celsius. I'm just going to write down and record my temperature into this column here. So I've got a series of experiments. Experiment number and then the volume of P. That was the one that I pipette out. That was the potassium hydroxide, I believe. P was potassium hydroxide. P was potassium hydroxide. That goes in the cup. And I started out with 25.0. In fact, all of them pipette out 25.0. I'm just going to change the volume from the burette from 5.0 to 10.0 to 15.0, etc., etc. But what I have is initial temperature. Initial temperature just now was 22.0 degrees Celsius. Initial meaning at the beginning. So that's why I fill in 22.0 degrees Celsius there. I am now going to add some distilled water because what they want me to do is measure 5.0 cm³ of Q into a measuring cylinder. So I have a measuring cylinder. I should wash this with some distilled water. Okay. After I wash it with distilled water, what do I need to do? This is a 25 cm³ measuring cylinder, not very accurate. I'm going to pass 0.0 all the way to 5.0 because I just want 5 cm³ of this burette reading. Okay, so we'll pass it very, very gently. So let's see, you should be able to see my view here. So I'm just going to pass it and I just need 5.0. So I will pass it and then I will be slow at around 4.0. So I will slow down now and then I'll do drop by drop because I am accurate using a burette. Okay, a burette is really, really accurate to 1 decimal place. As you can see now, this one is, can't really see it probably. Nope, let me just zoom out a little bit. This one is now, the background is terrible actually. This one is now 5.0 because I started from 0.0, so I have put in 5.0 cm³ of this solution acid, the sulfuric acid in here, and then I have to make it up, add water until I get 25 cm³. So this is called serial dilution. I have 5 cm³ of that thing from the burette, and I have the remaining 20 cm³, which is just distilled water. When I add distilled water up to 25 ml, I do not want to squeeze it all the way until 25 ml. I want to squeeze in so that it's fast, but then when you reach around 20 something, do not go fast. Instead, open the bottle and start using a dropper. This is a dropper. You add drop by drop towards the end, just like you make up a stock solution. You do drop by drop towards the end because you don't want to miss it. You need to get it accurate, well, as accurate as the measuring cylinder allows you to be. So just be able to do it. And measuring cylinder is not the most accurate thing in the world, but at least you can get it to 25 ml, 25 cm³. That's the best you can do. All right. Now we're ready to pour this mixture into the plastic cup, the styrofoam cup containing P. Let's just read the temperature again because it's important. It's still 22.0. It's still 22.0. So I'm gonna put it in there now. Okay. And then stir it with the thermometer. Measure the highest temperature reached. So the temperature is slowly increasing. It is now around 25, 26. Not too sure if you can see it clearly. I don't think you get to see it very clearly though. Okay, but it is increasing in temperature. So just now was 22, now it's around 25, 26. So I stir it for a bit. I need to record the highest temperature. So my eye is looking down that level, or I can flatten it up and then read at this level. So that is 26.0 degrees Celsius. So I read 26.0 degrees Celsius. Let me just lift that up so that you can see it clearly. I'm gonna hold it against these backgrounds and hopefully you can see it. Nope, that doesn't help at all. Does it help? Maybe not. Okay, it's 26.0. I think the white background helps a bit better. I should really grab a white towel, I guess. Let me. That is much better. So white background, you get 26.0. Okay, so you get the 26.0. So you see the silver, the line inside the thermometer. 26.0. Okay, so I'm going to record that as the highest temperature, 26.0 degrees Celsius. When you do on your calculator, the calculator will calculate temperature rise, final temperature minus the initial temperature. Oops, sorry, where was it? Nope, that doesn't work out quite well. Final temperature minus initial temperature. When you press 26.0 minus 22.0, you will get 4 on your calculator. That's because your calculator cannot tell you the decimal places. When it's 0.0, you need to use your brain and think a little bit and include the 0.0 because all of the temperatures are to the nearest 0.5 degrees Celsius. Okay, so without showing you everything on the screen right now, I'm just going to continue the rest minus the 28.0, which I stopped just now. That is 20.0 inside the measuring cylinder. I need to be careful. I don't want to, run anything over, because if I run anything over, I will have to start from the very beginning, and I don't have that luxury of time. So do not try and knock anything over, because you will not have time to repeat your serve, I guess. So here I'm just making it up to 25 cm cube, and that is 25 cm cube. I'm ready to mix it. So this one reads 22.0 as well. Put it in, and my temperature has gone up, and it is not as high as before. It's only around 31.0. 31.0 is the highest temperature. I started with 22.0, I end up with 31.0. That is 9.0 degrees Celsius difference only. Okay, so obviously in the real exam you're just collecting data, but make sure the temperature are all to the nearest 0.5 degrees Celsius, which include the temperature change to the nearest 0.5 or 0.0. Well, to the nearest 0.5 means you must have 0.0 or 0.5 degrees Celsius. Now we're on to the last thing that we're going to do. So just very quickly, rinse it with distilled water as well. Alright, okay. So the last thing I'm going to prepare out another 25 ml, another 25 cm cube of solution P. Do not get your solution mixed up. It's going to be a disaster if you get your solution mixed up. This is P, potassium hydroxide. You read the questions before you actually do the experiment so that you will not get confused. You do not have the luxury of time. As you could see, I'm rushing towards the end. I'm trying to portray to you the actual situation. If you're doing this actual practical, this is how rushed it will be towards the end there. It's not like the normal titration where you are supposed to get similar kind of titer. This is a different kind of titration. This is called thermometric titration. You don't know what the endpoint is going to be because you're going to use the data to plot the graph where they intersect later on. Okay, I have to top up my burette as well because the last thing I'm going to do is 25.0 cm cube in here. So I need 25.0 cm cube in the burette. Instead, I have only a couple of last drops in there. So Q goes in the burette. I wonder if I have enough. Oh yeah, I do have enough, okay? But in exam they said that each student should have a specific quantity, so you don't have time to repeat any of these at all. So I'm just gonna put this down to. So I've got it down to 23 cm cube. So that one is 22, this one is 23.0. 23.0 plus 25.0 is going to give me 48.0. So very clearly, I'm just going to stop at 48.0. So again, this is empty, kind of empty I guess. So stop at 48.0. Oops, sorry. So this is the very last thing. We're just getting ready for the very last experiment that we're going to do to monitor this temperature change when this acid reacts with this base. Any acid reacts with any base in a neutralization reaction. Every single neutralization reaction has a H plus aqueous combining with OH minus aqueous. It's going to be exothermic reactions. Neutralization is an exothermic reaction. Temperature of the solution, which is the surrounding, will go up because the system releases energy to the surrounding. The surrounding gets hotter. You see an increase in temperature. So I started from 23. So 23.0 plus 25.0 is 48.0. So nearly there, nearly there. I don't want to read below the minuscule, so I'm just going to lift this up a little bit. So then I'm reading with my eye level. So 48.0, and there's 25 mil, 25 cm cube. Oh, I forgot to read the initial temperature actually. Yep, it's still 22.0, pretty much the same as all the other experiments. Mix them in, and it's gotten a bit hotter because it's obviously exothermic. And it is reading 30.0, 30.5, 30.5 there. Okay, so 22.0 to 30.5, that is 8.5 degrees Celsius difference. So for that 12 marks, I've just done a series of experiments where I have pipetted, the same volume of the KOH, and then I run a different volume of the sulfuric acid from the burette, and I top it up with my distilled water. But the total volume of the sulfuric acid and the distilled water changes because I'm doing serial dilution. I'm slowly getting it more and more concentrated because previously I used lesser of the acid and I used more of the water, and now in the very last experiment I just have completely the acid on its own without any water. There's just the actual concentration of that solution we're provided with. So welcome back again, everyone. So we already got the experimental results from the experiment I just did. We can see the temperature rise. We have to express it to the nearest 0.5 degrees Celsius, as I mentioned, something 0.0, something 0.5. Your calculator will not tell you when it's 0.0. You need to keep an eye out for things like this, especially things like this. You need to be very careful. Now plot the graph of temperature rise against volume. This is y-axis, and then this is x-axis. Y-axis is vertical, x-axis is horizontal. Use these points to draw two intersecting straight line. The idea there is straight line, and they will intersect. So these have been given to you with the units. If you are asked to come up with a scale and label these things, this might be worth 4 to 5 marks. Now this thing is started out with volume of cube, 5.0 cm cube and 4.0 degrees Celsius. So 5.0 cm cube of cube and 4.0 degrees Celsius. So put a cross for the actual data. Now that first one is done, and then 10.0 and 7.0. 10.0 and 7.0, so that's that. Next up I have 12.0 and 8.0. 12.0, so there's 11, that is 12.0 and 8.0. And next up I have 16.0 and 9.5. 16.0 is there, and 9.5. 9.5, so in between 9 and 10, so exactly somewhere there. So follow your experimental data, yeah? 18.0 and 9.5, 18.0, 18, 17, 18. So there is 18.0 and 9.5 as well. So that is just going to be there as well. And still have two more, 20.0 and 9.0. 20.0 and 9.0 is there. And last but not least, 25.0 and 8.5. 25.0 and 8.5, in between 8 and 9 there. Okay, so these are real experimental data. When you don't add any Q, so when there is no Q added, so no Q added. If there is no Q added, it will start from 0. You've got to explain why. No Q added means no neutralizations. If you don't have any neutralizations, you don't bring about any heat transfer, any heat change, and therefore there is no change in temperature. And that is why this line has to cut through 0, 0, because always think about what does it mean when the x-axis is 0. So I got to draw a best fit straight line, but it doesn't seem like I want to go a best fit straight line. So perhaps that's what I could do there. But then you could also be thinking about another scenario where it looks like that is the best fit straight line there. Okay, so you got to be thinking, okay? So there are probably two ways about these. when they don't ask you about this 0, 0, you could potentially get there, but then it doesn't quite make sense because of what happens in reality. What happens in reality is this will cut there, and when you don't add anything, why should there be any temperature rise? Even though this is a better looking line for all the points, but it doesn't quite flows with the logic in terms of what happened when you don't add anything from the burette, no neutralization, no heat there. Okay, so I'm doing my best to try and get this slime to pass through as many of the points as possible to have a best fit straight line there. Okay, so hopefully you get what I'm trying to say. So what I'm trying to say is I am drawing this black color or the previous pink color line. If I draw like that, there are some points which are way off. If I draw like that, there are some points which are way off. I want to be somewhere in the middle where I'm as close to almost all the points as much as possible. The other point I'm thinking about is definitely the one where it kind of decreases already. So you can see that that is alright, but that one is missing the point on the very last point. That is alright, but that's missing the point in the middle. So go somewhere in the middle where it's not too far out from that and not too far out from that. And we can see there's an intersection now. And this intersection is where I'm gonna show on the diagram, show on the line, use your graph. So this graph where they intersect, they produce this 10 degrees Celsius maximum temperature. So I show there. So this is 10.0 degrees Celsius to the nearest 1 decimal place in terms of this reading there. And this one here is, so there's 15, there's 16, there's 15.5. So this is 15.25 cm cube. Like that, okay? So read the volume of Q where the two lines cross. If I am you, so 15.25, if I look at the next number, then I can round this up to 15.3 cm cube. So there's 15.3. As you know, about 1 decimal place burette reading in O-level, IGCSE level chemistry. Okay, so there's 15, there's 16, there's 15.5. This is in between, it's 15.25. Run it out, 15.3, 1 decimal place there. In part D, so your answer to C is the volume of Q that neutralizes this much volume of P. So looking back at the original question, what was P, what was Q? The P was the potassium hydroxide. P was what you pipette out. P is potassium hydroxide. Q is 1.12 mole per dm cube sulfuric acid. So Q was 1.12 mole per dm cube sulfuric acid. What do you want? You have the volume of Q, which was 15.3 cm cube according to your intersection from your graph, and then we want to find the volume of KOH. And do we have the volume? Yes, we do, because P was the KOH, P was the potassium hydroxide, and that was 25.0 cm cube. And your job is to find the concentrations of the KOH. So looking at these informations, what do I need to do? I need to really have mole ratio. So I want to find something on KOH. So the mole of KOH is to the mole of the sulfuric acid. This is equal to the ratio from the balance equation. So 2 mole of KOH, 2 moles of KOH, and then reacts with 1 mole of H2SO4, 1 mole of H2SO4, and this is equal to the actual reacting amount. So these are solution chemistry, so we're dealing with concentration time volume, but be very careful. This is concentrations in mole per dm cube, which means that for your unit to cancel out and basic mathematics, you need this volume to be in dm cube instead of in cm cube in order to give you the overall unit of mole as mole there. So we know that 1 dm cube is 1000 cm cube, so whatever cm cube you have has to be divided by 1000 in order to convert that to dm cube. You can do this on your calculator by multiplying by 10 to the minus 3. That's exp minus 3 on your calculator as well. So the mole of KOH is going to be concentration of the KOH multiplied by 25.0. You can do 25.0 divided by 1000, or you can do times 10 to the minus 3. On your calculator, you will press 25.0 exp, the button exp. It means times 10 to the power of. And then after exp, you key in minus 3, and that will be the function there times 10 to the power minus 3. At the bottom, I have 1.12 mole per dm cube, concentration of the sulfuric acid, and this is multiplied by 15.3. Again, have to be converted into dm cube by dividing by 1000, or you can do times 10 to the minus 3. So your job now is just rearrange the equation to make the concentration of KOH the subject, move everything at the bottom, the denominator, to the left hand side. Then you're going to multiply the denominator by everything on the left hand side. So there's 2 over 1. That overall thing does not change anything because that overall thing just multiply by everything at the bottom. So there's time 1.12 times 15.3 times 10 to the minus 3. However, I have concentration of these times 25.0 times 10 to the minus 3. So realistically speaking, I'm going to divide the whole thing. I'm going to divide the whole thing by 25.0 times 10 to the minus 3. So I'm allowed to do this now, where I can move this information up there because I'm slowly running out of space here. So I'm just going to move these all the way to the left side so that I'm not really running out of space there. So where do I get this number from? I get it from this bit here because I just want this as the subject. So I'll move all of these down to the bottom denominator. Do things with bracket and you should be all right. So you would do the top bit first in a bracket. So 2 over 1 times 2 over 1 times 1.12 times 15.3, press exp minus 3, or you can do 15.3 divided by 1000. It's the same thing. I get 0.034272 on my calculator, divided by bracket 25.0, divided by bracket 25.0, exp minus 3, I get 1.37088. They want our answer if you read the question. Of course, you would have read the question from the very beginning, right? So this is to 2 significant figures. So we have 1 and 2 significant figure. We look at the third one, that is greater than 5. So this one gives you 1.4 mole per dm cube, unit of concentration, and this is to 2 significant figure as required by the question there. So in this part E, how has heat loss been reduced in this experiment? So this is talking about something that you have done. You have already done this. We have already done this because it said, what have you done? You know, we have already done this. So what have you done that have, reduced heat loss? Earlier in the experiment, if you think about your procedure, we have supported this plastic cup. Actually, it's a styrofoam cup supported on a beaker. Styrofoam is an insulator. So if you have used a plastic cup, which is an insulator, and that would have provided you the first, the first barrier against heat loss there. But of course, in terms of improvement, we can further insulate by having a plastic lid, by insulating the outside layer there. But that is just the idea of insulation to further prevent heat loss, and that is related to the next bit. But let's just answer this question first. What have you done to reduce heat loss? We had used a plastic cup, or you can say a styrofoam cup, and this is an insulator. So that means it doesn't allow you to conduct heat easily. Suggest 2 ways in which the accuracy in terms of the change in temperature, because your delta T is greater than 0, as this is a neutralization reaction, and you know about the ionic equations I explained earlier. It will just give you water, the combination of H plus and OH minus just forming bond without breaking bond. Exothermic reaction, give out heat. That's why your temperature of the surrounding rises. And how can you make the temperature rise more accurate? How can you improve on the experiment? So we know we can further reduce heat loss. So you can only use this once. You can only talk about reduce heat loss once, but they want 2 improvements. So how can you further reduce heat loss? Use a plastic lid. You want to use something which is an insulator to cover the cup. How else can you improve the accuracy? So I saw from a couple of students' result that when they did this experiment, their initial temperature were not all really the same. Some were really different. So it turned out that some students did not wash the thermometer at all, and that is quite a mistake because the thermometer might still be warm from the previous experiment. If you had used it straight away in the next experiment without washing, you might have contaminated your new solution mixture as well. So by the end of these, when you wash and rinse your plastic cup as required, you should also rinse your thermometer as well, such that when you dip it into the new solution, it should have read similar kind of temperature rather than reading you something which is very, very far off. Another thing you could have done is that for each required reading, you could have repeated the experiment so that you will get two different temperature rise for the same experiment, for the same set of volumes. Then you can take the average of the two readings, which hopefully wouldn't be that far away, and this will further improve your accuracy. So as I did mention, you could have repeat the experiment, repeat each experiment, and then take average, and then average the temperature rises. Provided that you are a competent chemist, then your two temperature rises shouldn't be that different, considering that they are all based on the same set of readings. There are other possibilities. As I did mention, you could have checked or ensure or make certain that the initial temperature was the same. Initial temperature was the same, before starting the experiment, so that we are not influenced by the temperature of the surrounding or whatnot. Of course, there are other possibilities as well, but one thing which is not accepted would be stirring, because in this kind of experiment you're expected to stir once or twice and then you just leave it be, because the more you stir, the more the heat get distributed, and therefore it will not have given you a more accurate temperature rise. It will have been less accurate actually if you stir more and more. And another thing is some students will have said that you wait for a long time before you read the temperature. That is not going to be accurate, because if you wait for too long, if you wait for several minutes, your temperature of the solution might have cooled down, and that might not have led to a more accurate reading. That might have led to a less accurate reading actually. Okay, I think there are many other possibilities, so whatever you thought of, as long as it makes sense, as long as you make the experiment result more accurate, you should be alright. But the one thing that you have to remember is about reducing heat loss, but there are some other tricks that you could have used. Actually, I just remember there's one more. So earlier, remember that we had used a burette. We had used a burette to measure the volume of Q. We use a burette here, but the volume of water was using measuring cylinder. If you think about it, we have tried to be accurate with the volume of Q, but then we have used measuring cylinder, which is way less accurate than a burette, to measure the volume of water. So to get a more accurate volume of water, we could have used a burette to measure out the distilled water as well. So there's another one. So use a burette to measure the volume of the distilled water. And if you have gotten all the volume measured accurately, then you expect the reacting volumes of solution to be more accurate, and therefore this will result in a more accurate temperature rises. That's it ready for this 21 marks overall thermometric titration question. Thank you for watching. Don't forget to click the button on the bottom right to subscribe to my channel. Follow me at ptet.chemistry. There's at ptet.chemistry on Instagram, Facebook, Twitter, and Telegram to get connected. I'll see you in the next tutorial video. Thank you for watching.